I will begin. Ahem. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. So thank you for your homeworks. I will tell you this. For problem 88, here's the solution. So if you want to associate to a linear transformation, if you have a linear transformation that goes from V to V, and you want to associate to that a matrix, right, in a bijective fashion, well, the natural candidate for that's just the coordinate matrix. Pick a basis for your vector space, given to be dimension n. Then the assignment of T maps to T beta beta, well, that's actually going to give you an isomorphism from linear maps on V to n by n matrices over F, assuming, of course, that V is an n-dimensional vector space. That's, be like, well, how did you think of that? I don't know. You guys asked me questions. I thought about it, and I said, oh, that's the map, right? I have to think about it. It's not something that I go, oh, here's the algorithm for constructing an isomorphism, and I just write that down. I mean, no, you have to, you dwell on these things. You learn how different things are constructed, how they work, and then when you're asked a question, you respond in kind. It's a creative leap to write psi of T is the matrix T beta beta. There are other ways to define the map. I don't think I thought of doing it that way in a past semester. In a past semester, I gave a more complicated description of the isomorphism, all right? So generically speaking, if you're trying to find an isomorphism from one vector space to another, one surefire way to do it, they won't let you down, is if you can find a basis for your first space, and if you can find a basis for the other space, all you got to do is define a map by mapping that basis to the other basis, one at a time, and extending that map linearly. That will define an isomorphism. So there is a totally unclever and very laborious way of constructing an isomorphism, right? That's probably not the right way. The right way is just to try to gain a conceptual understanding of what isomorphism is so you can just write down maps. If you look at my notes, I have many examples of isomorphisms. Look at those. See if you can understand them, right? Okay, anyway. So today, I'm talking about dual spaces and the cosets dual space. Dual space and cosets, and perhaps quotient space. We'll see if we get there. I should probably put a question mark on that last thing. We may or may not get there today. But this is the direction we're going here. So I'll start with a definition. If V is a vector space over F, then the dual space to V is linear transformations from V into the field. All right. Moreover, we denote V upper star, that's V dual, that is this space. Okay, so that's our notation. We get sick of writing linear transformations, set of linear transformations from V to F. So instead, we'll just say V star. That's what's called dual space. And dual space allows us to discover things about the given vector space which might remain hidden from another viewpoint. So I'll try to explain that, how that works out. To start with, I'll just give you an example. So let's look at the vector space of continuous functions on the closed interval from 0 to 1. Okay. Is that a vector space? Is the sum of continuous functions on the closed interval 0 to 1? Again, a continuous function on 0 to 1? Yeah, sum of continuous functions like that, still a continuous function like that. Scalar multiply, continuous function, is it a continuous function? Yep. So this is a subspace of function space that we can look at. And I can, suppose G is, suppose G is an element of V. Then define T of F. What it's going to be, I'm going to say it's the integral from 0 to 1 of G times F dt. if you want me to be more, you know, what's the word? Pedantic, perhaps. Notation I would often use in calculus would be the more annoying, but probably technically correct f of t, g of t, f of t dt, you know? I'm looking at g and f both as functions of time and integrating time from 0 to 1. But I'm not going to write of t because it just gets old, all right? So my claim is this. T is an element of V dual. T is an example of what's called a linear functional. Okay. By the way, these things are linear functionals. All right, so what do we have to check to show it's in V dual? We need to check T of C1 F1 plus F2, right, and see how that works out. So that would be the integral from 0 to 1 of this function g times CF1 plus F2 dt. But by properties of definite integrals, I can pull the c out. I've got gf1 dt plus the integral of gf2 dt. So just using properties of definite integration of continuous functions, calculus 1, right? There it is. That's c t of f1 plus t of f2. So that calculation, of course, will supply additivity and homogeneity for my t, right? So this t, this transformation, is in fact what's called a dual vector. So this t is also known as a dual vector. Vectors in the dual space are called dual vectors. All right. Now this example is pretty flexible, right? What are your choices for g? What could you make g in my example? I'll put it right here. Remark. G is anything, right? Anything in C01. It could be anything. How many choices are there? How many continuous functions are there on 0 to 1? 3? No. No one said 3. I just made that up. It's fun to think somebody said 3, though. That would be infinitely wrong, right? I mean, this vector space is an infinite dimensional vector space. And you know what? The dual is also infinite dimensional. Even this one example allows for infinitely many distinct dual vectors. And that's not all that there is. There are other dual vectors. How about this? If you take t of f and just define it to be f of 0, that's a dual vector here, because you can check that this is linear. If I take cf1 plus f2 of 0, that's c times f of 1 of 0 plus f2 of 0, which is the needed property to get linearity for that different dual vector. So my point to you is that in this case, the dual space and the vector space is infinite dimensional. Now, infinite dimensional vector spaces are kind of tricky. So this is just a bit of, well, terminology, let's say. Terminology. If the dual of the dual, the so-called double dual, is isomorphic to V, then V is reflexive. I think that my first example is not a reflexive vector space. If I take the double dual, I don't get something isomorphic to V. I get something much bigger. So dual space in the infinite dimensional context is like pretty tricky. However, V double dual is isomorphic to V given V is finite dimensional. Okay, so this bullet point is what I'm going to expand on in the next about 10 minutes of lecture. I'm going to explain to you why the dual space of a finite dimensional vector space is in fact finite dimensional. I really don't need to, I mean, I think we already know that actually if you just look at theorems we already have. We talked about what's the dimension of linear maps from V to W. Do you guys remember that? What was the dimension of the set of linear maps from V to W? It's the dimension of V times the dimension of W. If you want, there's an obvious isomorphism. Psi of t is the matrix of t beta gamma, where t, of course, is a linear map from V to W. And I'm saying that V has basis beta and W has basis gamma, right? That's also an isomorphism. In the same sense, problem 88 was a simpler case of that. I took the domain and the codomain both be the same vector space, so we get to say more there in that problem 88. We also get the interplay between multiplication and composition. That's that algebra structure I talked about. But anyway, getting back to here. My point is, this we know from our previous work, you know, the dimension of the linear maps from V to W. Supposing V and W are finite dimensional, right? It's just the product of the dimensions because it's the same as the size of the matrices which represent these things, which is m by n matrix is an n dimensional space. So here, right, if V is n dimensional over F, F is what dimensional over F? F is one dimensional over F, right? So we have n times 1 is the dimension of the linear maps from V to F. So that says that the dual space has dimension n, just like V has dimension n. They have the same dimension, so they're isomorphic. Okay, but that, I want something with a little bit more structure than that. I mean, we could just do dimension counting to prove that they're isomorphic, fine, but there's something more. Definition. If beta, V1, V2, Vn, is basis for V over F, then beta star is equal to V upper 1, V upper 2, V upper n. So I'm defining these symbols right now, okay? These are not powers. They're just superscript labels, okay? Are defined by V upper I, V lower j is equal to Kronecker delta ij for all I and j, 1, 2, n, you know, extended linearly. So this beta star is the so-called dual basis to beta, the dual basis. All right. So let me, you know, what do I mean extended? Extended linear means what? What do we mean extended linearly? So let's work it out. Vi, right, of x, what should that be equal to? So let x be an element of the vector space, okay? By the way, from this point on out, we're assuming the vector space we're thinking about is finite dimensional, okay? So I wanted to make a parting comment about the infinite dimensional case. If you go on in math, you'll take a course called functional analysis, and there we deal with duals in the infinite dimensional context. It turns out you need to bring in other questions of analysis to manage the dual space. You don't look at all duals. You just look at the continuous ones. Those turn out to be equivalent to the bounded ones. And there's a whole interesting story. That's functional analysis. But we'll keep it finite dimensional. So how do we what does it mean to extend linearly? That means that we are assuming that this VI is a linear map. So to exploit that, we'll expand X in the basis. And I'm going to use C sub i's for the moment, but I will soon give up on that notation, okay? So Ci Vi, 1 to n. I'm assuming that it's linear, so that means I can pull out the sum. I mean, this is by construction of the map. I'm extending linearly. Oh, bad choice of I. How should we fix this? Make this, which one should we make a J? I'll give you a choice. You can either do these or those. These ones, okay. There we go. So V upper J of V lower I. So what is this? This is by definition the Kronecker delta ij. So what's Kronecker delta ij do to the sum? Here J is a fixed but arbitrary index, you know. So it has to be in the answer. I is a dummy index of summation. It's going to go away. So we keep the J, get rid of the I, and we just got C sub J. That's what happens here. This is C sub J. What is this? What is this dual basis vector? What's the meaning of Vj of x? What if I wrote the coordinate vector of x with respect to the beta basis? What is it? It's C1, C2, Cn, right? So what's the jth component of the coordinate vector? Cj, what else is it? It's V upper J acting on X. So this is what the dual basis does. It selects components of vectors with respect to the given basis. It's actually a way of ripping apart the coordinate map into its pieces. The dual basis is like little bits of the coordinate map. String them all together, you get the coordinate map. So because of this, we introduce a new notation. So notation. We will now write x is equal to the sum I equals 1 to n of x upper I, V lower I. So we put the index up. And with this new notation, you can see what? X upper I is actually nothing more than V upper I acting on X. So essentially we have the following theorem. For X in the vector space, we can write X as the sum I equals 1 to n of V upper I of X times V lower I. See, because V upper I of X is the component with respect to the beta basis of X. Now, I mean, there's another theorem. I've used the word, I've called it a dual basis, right? But you can prove beta dual defined by Vi Vj equal Kronecker delta ij extended linearly serves as basis for V dual. All right, and what's the preamble to this theorem? I'm given V with basis what? Beta. Okay, So given a basis beta with vectors v1 through vn, lower 1 through n, we define the dual basis to have the upper subscripts defined to be Kronecker delta on the basis, and extended linearly, this defines the dual basis. And in fact, it is a basis, right? What does it take to prove this theorem, that beta star is a basis? What do we need to prove? Yeah, linearly independent and spanning, right? So let's see here. What do you guys want to start with? The spanning or the linear independence? Let's start with the spanning. How about that? So I like to use alpha for dual vectors. Let alpha be in V dual, right? So alpha is a linear map from V to F, right? By construction, by definition of what dual space is. Let's let X be an element of V, all right? Calculate alpha of X. What's that equal to? Well, that's equal to alpha of the sum, right? I equals 1 to n of, let's say, x upper I, v lower I, right? I mean, that's the basis expansion for x. Listen, guys, the reason I have been using C's for the components of a vector up till now is to avoid confusion with the Cartesian components of a vector, because a lot of our examples have been in Rn. In this abstract context, there's no danger for confusion. I'm just using x1 through xn for the components with respect to the abstract basis beta. You know, I didn't do that up to this point precisely because there would have been a confusion between that and the given Cartesian coordinates, x1 through xn, right? I'm just saying, that's why we've kind of changed notation a little bit. But anyway, so alpha is a linear map, right? So we can pull out the sum, we can pull out the constants. What's that look like? So we got ourselves an alpha of vi and xi. I'm going to write the multiplication. This is technically speaking, we never really defined multiplication on the right of vectors in a vector space, right? I mean, if you want me to be fussy, we defined c times v, right? Scalar multiplication of a constant times a vector. What should we mean if we have v times c? What would that be? What's the relation between these? If you want to talk about right scalar multiplication, how do you do it? There you go, fixed. So we can talk about right scalar multiplication. We just assume it's equal to the left, right? And that's just a notational convenience for us. You know, I bet you've already done it without thinking, right? You've written scalar multiplication on the right somewhere, even though we only defined it on the left. Think about it. Did you do it? I bet I did it somewhere. So let's just, let's be honest with each other. We're allowed to do it, and it's defined like that, okay? Anyway, so I did it right here because I pulled the constant out to the right. The reason I did that is because then I rewrite x upper I in view of what I just learned up here, which is that x upper I is vi of x. So what do I have? I got the sum, I equals 1 to n, of alpha sub vi, v upper I, acting on x. But I can rewrite this as a sum of maps. This is the sum of the maps, I equals 1 to n, of, let's say, alpha sub I, all right, v upper I, acting on x. And what did I just define alpha I to be? Alpha sub I equals definition what? Alpha acting on what? Vi. So the alpha sub I would be the ith component of the dual vector. But look at this equation. What does this equation say? We got alpha of x is equal to this map, sum over I 1 to n, alpha sub I of v upper I, acting on x. This is true for all x in v, right? So what's that tell me? That tells me that alpha is equal to the sum I equals 1 to n of alpha sub I v upper I. That says that any dual vector is in the span of the dual basis, right? This is an element of span, right? So thus, V dual is a subset of span beta star. Can you guys tell me why the other direction's true? Why is the span of beta star a subset of V dual? That's what I need in order to get equality there, right? So beta dual has what in it? You just got to think through it. I don't even write anything down. We'll just use words. Beta dual is a collection of these maps, V1 through Vn, right? By construction, these are linear maps. I constructed them by linear extension. They are therefore linear maps. What is the span? The span of this is a linear combination of linear maps. We have proved that the sum, indeed the linear combination of linear maps, is once more a linear map of the same kind. It follows that the span of beta star is a subset of V dual, because everything in the span of linear maps is again a linear map of the same kind. So therefore, we have that the span of beta star is equal to V star. Now that doesn't quite prove it's a basis yet, does it? What else do we need? We need linear independence, right? So, yeah, question? Oh, no, yeah. So let me recap here. Definition: alpha in V dual has alpha sub I equal to alpha of VI, right? Where I equals to 1 to n. And we just proved theorem that alpha is equal to the sum. I mean, I don't know, it's hardly a theorem, but the sum I equals 1 to n of alpha sub VI, V upper I. Right? Okay, so now let's attack the linear independence directly. In linear independence of beta star. So I'll be rather boring. I'll just do the usual thing. Suppose we have the sum I equals 1 to n of, let's say, C sub I, V upper I equal to 0. I want to show that all the C's are 0, right? That will prove linear independence. So how should I get that all the constants are 0? If this doesn't float your boat, we could rewrite it this way: C1 V1 plus C2 V2 plus Cn Vn. I'll do that. Sometimes that helps students to write it that way. I don't know why, it just does. This is a function equation, right? The V1 through Vn, these are all linear transformations on V. That means we can take this equation and we can evaluate at a vector in V. What's a smart vector to evaluate this equation, soon to be labeled star by? 0? Well, 0 will give us 0 equals 0, which is true but useless, so no. I mean, 0 is always a vector, but there's other vectors that are kind of important here. In fact, this whole discussion is centered around this particular set of n vectors, the basis, right? So why don't we take star and evaluate on, let's say, Vj. So like C1, V1 of Vj, right? Eventually we get to Cj, Vj of Vj, Cn, Vn of Vj. And what happens to that sum? The 0 map on Vj, by the way. So what we get is just Cj times 1 is equal to 0. Because by construction, the dual basis acting on anything except for the corresponding basis, it's literal dual. All of those are 0 except for when j matches, in which case we get 1 by construction. But Cj being arbitrary, C1 equals 0, and so forth and so on, Cn equal to 0. Therefore, beta dual linearly independent. And there you go. We have proved that the dual basis is in fact a basis. So it would be embarrassing if I named it the dual basis and it wasn't actually a basis, right? That would be very embarrassing, wouldn't it? So that's not the case, though. Any questions? Here's a question. I want you guys tell me how to construct an isomorphism psi from V to V dual. How would you construct it? What's the possibility here? Continuing with our discussion so far, suppose you got the basis beta, right? We just proved that beta dual is a dual basis. How can we define an isomorphism? I said at the start of class, this would be an isomorphism. We just take psi of V lower j and map it to V upper j. And then extend linearly. That would give you an isomorphism. All right. Here's a theorem. If we look at V equals to Rn, all right, then if alpha is in the dual space to Rn, all right, Rn dual, I'm sorry, if, I didn't need a then, I needed an and, all right, here's the then. Then there exists W in Rn such that alpha of x is just equal to W dot x for all x in Rn. In other words, every dual vector of just plain old Rn can be realized as the dot product of some fixed vector. And so you guys know that you can write that as W transpose x, right? Row column. So for that reason, sometimes people will talk about alpha sub W of x being equal to that. So in other words, the dual vector alpha sub W naturally corresponds to W transpose, right? Which is, by the way, an element of our 1 by n. This is why sometimes people will refer to the dual space as row vectors, because there's this natural correspondence between row vectors and dual vectors. I don't tend to do that, but it's something that it's in a lot of people's thinking. Let me just put a little thought bubble around here. So the proof is actually pretty nice. Here's the proof. If we have alpha as a linear map from Rn to R, just consider alpha of, alpha of x, right? That's going to be alpha of the sum of x upper I, e lower I in our current notation, right? And so by additivity and homogeneity, I can pull out the sum. Right. So if you look at that, that's exactly x dot W for W equal to what? alpha of E1, alpha of E2, alpha of En. In fact, I could even be a little bit more explicit here. Really what's going on in terms of our current notation is that alpha of x is equal to, it's equal to x dotted with the coordinate vector, in fact, of alpha with respect to the beta basis, beta dual basis, rather. That's really what you're looking at here. See, because this right here, what's this show? This shows that the coordinate vector of alpha, right, with respect to the beta dual basis is nothing more than alpha of V1, alpha of Vn. So there's that. Coordinate change is very interesting for dual space. So you guys seem a little worn out. I don't think I'm going to go through that today. But I'll just tell you the big picture. I'll tell you the result. The result is this. If you study coordinate change, what you'll find is that the basis for vectors changes in the same way as the components for the dual vectors. And the basis for dual vectors changes the same way as the components for vectors. What I'm saying, in other words, is that the objects written on the board, which have upper indices, change in the same way. If you change the basis, the x upper I will change by the same matrix as the v upper I. And the alpha lower I, these guys, the alpha lower i's will change, if you change coordinates, those will change in the same way as the v lower i's. All right. So in physicists' classic language, they would say that vectors with upper indices are so-called contravariant vectors. Contravariant versus x lower I, or well, let's say alpha lower I in our notation, be covariant. And in fact, if you read physics literature back from the time, Einstein wrote these things down and popularized them in general relativity, what you'll find is that they didn't talk about a basis for vectors or for covectors or for dual vectors. All they would do would be talk about the components and how they transform under coordinate change. That's the whole concept of a vector for them. But anyway, I can tell you more if you want to talk about it in office hours, but if I think it's right, I'll come back next time and actually give you the calculations to prove what I just said. It's straightforward, but it's easy for you guys to get lost in circles. I have some notes that I wrote on this that I'm going to scan and post for you guys. So the page 5 actually has the details of what I was just talking about. Okay, so next time if I think it's right, I think it's wise, I'll cover that for you. Let's see here. So moving on, we can also rip apart a linear transformation from V to W. And this might be a good exercise for us just to bring together everything we've been doing so far in this lecture, notationally. Suppose you have T, a linear transformation from V to W, all right? And I'm going to let beta, as usual, be my basis for V, n-dimensional. I'll let gamma, W1 through Wm, be my basis for W, and correspondingly, beta dual, V upper 1 through V upper n, and gamma dual, the dual space to W, W upper 1 through W upper m. All right. And what I want to just show you is that we can rewrite the linear transformation using the dual basis. We can rip it apart into component functions using this dual basis technology. So here it is. T of x is an element of what? T of x is an element of w, right? That means I can rip it apart in terms of the w basis. How do I pick out the jth component of the w basis? So like generically speaking, w is equal to the sum j equals 1 to, m of, let me not say w, let's say y. Y is equal to the sum j equals 1 to m of like w upper j of y times w sub j. Right? This is the component expansion in terms of the gamma basis. The gamma dual basis picks off the jth component, and then we take the sum of those. That's the reconstruction of y. I can apply that to t of x. So I've got w upper j of t of x times w lower j. That's just using that gamma is a basis for w, and that gamma star selects components with respect to that basis. Then what I'll do is I'll take that x, and I'll expand it in the beta basis. So x, of course, is what? Sum of what? Sum I equals 1 to n, right, of, and let's see here, we've got v upper I acting on x times v lower I. So there's the basis beta expansion for x. I still got my wj out here. My next move is simply to pull the scalars out and reorganize things a little bit. So what we're looking at here is the sum j equals 1 to m, sum I equals 1 to m. And if you look what we got, we got wj of t of vi, and I'm using that right scalar multiplication again because it's convenient to me, w sub j, and all I'm really doing here, guys, is pulling the sum out, because this is the composite of linear maps. wj is linear map, t is linear map, composite of linear maps is linear. I can pull the sum out. I can pull the scalar out, but I'm going to pull this scalar out. I'm going to pull it over here, right down here, right? And then I'm going to rewrite this whole thing as a sum of maps. So instead of looking at this just vi of x, I'm going to look at it of all of this of x. But this identity holds for each x in the vector space, and so we've derived the following result. We can write t as the sum j equals 1 to n, sum I equals 1 to m, I equals 1 to n of w sub j, upper j rather, of t lower vi. What did I do? Oh, no. Yeah, the I goes from 1 to n. Sorry about that. Thank you. M as in mommy, N as in nanu nanu. So there you go. Now, let's do some name calling. Let's call this A upper j lower I. What is that? What is A upper A lower I? Well, w upper j of t lower vi, I'm saying that is, by definition, I'm calling that my quote-unquote aj lower I, all right, definition. What else is it, though? How about this? What if we look at the matrix of t with respect to beta gamma? What's that? What if we look at the, what if we look at the jith component of that? So let's see here, column, right? I'm saying that's the column, that's the row. All right, so that would be, we're supposed to take, what's column I would be what? T of vi, right? We're supposed to take the gamma coordinate of that in this matrix, and then I'm supposed to calculate the jth component of this. How do you calculate the jth component of that? We hit it with W upper J. Aha! So in fact, this is nothing more than the matrix T beta gamma suitably denoted, the jth component of that. In this wild world of up-down indices, the matrix no longer has two lower indices. It's got one up, one down. So you can tell the difference between the row and the column index in this world of up-down notation. Yeah. I don't expect you to master the up-down notation for matrix, but I would like you to be aware of how it works for vectors versus dual vectors for the test. Like, I think the matrix is a bridge too far to expect you guys to understand. The use of the up or down indices as it relates to vectors and covectors, I think that I've said a lot about today. I think you've got a chance of, if I were to ask a question, you shouldn't be lost. Anyway, okay, so there's that. So that brings us to our next topic. Token example. If we take v equals to Rn by n, can you guys tell me a linear functional? Here, I'll give you two. Determinant of A, well, that's an element of the reals, right? The trace of A, that's an element of the reals, right? These both have nice properties. Which of these is in the dual space, and which determinant is determinant in the dual space, or is trace in the dual space? Which is, which isn't? So is the trace a linear operator from n by n matrices to the reals, if we're looking at real matrix? It is. The trace of CA plus B is the C times the trace of A plus the trace of B. Is the determinant of CA plus B equal to C times the determinant of A plus the determinant of B? It is not. So this, despite the fact that the determinant is giving us a scalar corresponding to a matrix, it's not a linear functional, right? It's something else. So, in summary, determinant, not an element of V-dual, but trace is an important example of a dual vector. We've already seen the importance of trace in previous lectures, right? So, all right, so this brings us to our final topic for today, namely cosets, which I'll just start cosets. All I'm going to do for you guys is draw some pictures. I won't even give you the formal definition of coset just yet, right? So, well, actually, I'll give you that. V mod W is the set of cosets. It's x plus W such that x is in V. Now here W is a subspace of V. So what we're going to look at next time is the fact that this gives us a way of looking at vector spaces in a new way. For example, we could look at V as R2. We could look at W as like the span of 1, 1, right? And so W, if I was to picture it in red, is this guy, right? It's a subspace. Now X plus W, on the other hand, is not a subspace. It's a parallel translate of this. So it's something like this. This, for example, would be 1, 0 plus W. Or we could look at this. Over here, here's another one. That's 0, 1 plus W. See, that's 0, 1. This was 1, 0. So if you look at it, the plane is chopped up into these cosets. I thought of another picture I wanted to share with you guys, and then I'll really shut up for today. I thought a way of drawing a picture of P2. Here's a picture for P2. I don't know why I didn't think of this earlier, but this is a picture of quadratic polynomials. I just take x squared 1 and x to be the different coordinate directions, yeah? And so if we take w to be the kernel of the, w is the kernel of the double differentiation operator, you know, d squared x dx squared, what's that? Well, you guys know, you just did your homework. That's the span of 1x, right? So in this picture, the subspace w is the, well, sort of the xy plane. It's this thing. And what do the cosets look like? They're a stack of horizontal planes. They're things like this. For example, this one up here could be x squared plus w. And then down here somewhere, we've got another, you know, minus x squared plus w, et cetera, et cetera. So we can take the vector space and we can basically divide it up into this stack of cosets. And if we think of those cosets as new vectors on their own, that gives us what's called quotient space, quotient vector space, which I'll describe the structure of next time. So, thanks, guys.